Hello all, welcome to EC Electronics. Recently an examination happened for the Department of Science, NESAC, that is Northeastern Space Application Center, for the post of Technical Assistant. That is on January 19th, the examination for Technical Assistant post happened for NESAC. And today we'll be seeing the questions from that examination. So the ISRO Technical Assistant examination is going to happen very soon. And I hope that this question paper discussion will be very much helpful for you to prepare for the ISRO Technical Assistant post also, because the NESAC is coming under the Space Center, that is Department of Space. Okay, so we are going to see some questions from the NESAC the previous year question for Technical Assistant. Okay, so this is a very latest question paper since the examination happened on January 19th. Okay. So in this part 1, we'll be seeing some question. We'll be doing the parts, part 2, part 3, etc. for seeing all the questions from the Technical Assistant examination for electronics. Okay. So let us see what is the first question. Consider the circuit shown below. If input is a sine wave of 5 volt, what is the output? Okay. So here the circuit is being given. This is the load. The circuit, if you see, there is a load, there is a diode, there is a voltage source of 2 volt. So what is this circuit? This is a clipper circuit. We have done a lot of videos for clippers. So if you have seen any of those videos, you will be able to find out that this is a clipper circuit. Now since this is a clipper circuit, it will be clipping off some portion of your waveform. So your input waveform applied is a sine wave of 5 volt. Okay. This sine wave of 5 volt is applied to the input side and we are taking the output from the output side. So let us see what is happening during the positive half cycle. Okay, during the positive half cycle of the waveform, the diode will get forward biased, right? But due to the presence of this 2 volt, it is making the diode as a reverse bias. So we won't get, the diode is forward bias and the diode is forward biased by VI and the diode is reverse biased by the voltage source of 2 volt. Okay. So during the shunt connection of the diode, that is the diode is connected in parallel connection. So in parallel connection, when diode is forward biased means we won't get any output. It will go to the input will go to the ground. But when the diode is reverse biased means we will get the output. So how will the output waveform look like during the positive half cycle? During the positive half cycle, till the 2 volt, the diode is reverse bias. Okay, so till 2 volt, diode is a reverse bias. But when the input is greater than 2 volt, since it is a sine wave, it will gradually go up to 5 volt. So starting from 0 up to 2 volt, the diode is reverse bias due to the presence of this voltage source. But after or beyond 2 volt, the diode is getting forward bias due to the presence of your input waveform. So what will happen? Clipping will take place at 2 volt. So this is your waveform. This is plus 2 volt. Now what will happen during the negative half cycle? The negative half cycle is making the diode reverse bias. That is VI or your input waveform is making the diode reverse bias, and also the voltage source is connected. In the previous case also, the voltage source is making the diode as reverse bias. So for both the cases, for input and for the voltage source, is trying to make the diode as reverse bias. So it will be in reverse bias condition only. So you will get your entire negative half cycle. So this is how your output waveform will look like. Now what is being given in the options? The options are A, full sine wave of 2 volt amplitude. No. Sine wave clipped at plus 2. Yes, plus 2 volt. It is a correct answer. Option C, full sine wave of 5 volt. No. D, sine wave clipped at minus 2. No. So the correct answer here is option B, which is sine wave clipped at plus 2. So your sine wave is actually clipped at the positive 2 volt. So the correct answer is option B is your correct answer. Next question. In 8086 microprocessor, that is the 8086 microprocessor has 20-bit address line. How many memory locations can it address? It is a very simple question. If n is the number of bits in the address line, then it can access 2 raised to n number of memory location. Not only for 8086 microprocessor, but for mostly all the processors. I don't know whether any processors is having some variation, but generally it is a case. That is, if n is the number of bits of the address line or the address bus, then it can access 2 raised to n number of address locations or memory locations. And what is the value of 2 raised to 20? It is equal to this value. 1048,576 is the value, and it can access 1048,576, this much number of memory locations. Okay, so the correct answer is option D is your correct answer. A 10 milliwatt signal is fed to an attenuator of 6 dB gain. Okay, what is the output power? That is, the attenuator is having a dB value of 6 dB. The input signal power is 10 milliwatt. What is your output signal power? Now, if you have to face such type of question, I'll give you a simple trick to answer these type of questions. Okay, so if the attenuator's gain is or dB value is 3 dB, then the power, we are talking about power, okay, the power will reduce to half the value of input. That is a relationship. Okay, now if it is a 6 dB attenuator, means your power reduces to 1/4 of input. Then if it is a 10 dB attenuator, means again your power reduces to 1/10. Then if it is 20 dB, means the power reduces to 1/100. So this is the simple relationship you have to follow. And if you know this, you don't have to go for any calculations, equations or anything. You can directly answer this type of questions. Okay, so generally they'll be giving any of these relations, any of these dB values, 3 dB most probably or 6 dB. Okay, so if the value is 10 milliwatt for the input power, and if it is a 6 dB, means 1/4, that is 2.5 milliwatt is the answer for this question. That is 2.5 milliwatt is the output power from the attenuator. Attenuator generally used for suppressing the signal, right? So the value of power, output power will be lesser anyways. So this much of degradation will be happen for these dB values. For 3 dB it is half the input, 6 dB it is 1/4 the input, 10 dB means 1/10, 20 means 1/100. Okay, so this is the relationship, and the answer for this question is A, which is 2.5 milliwatt. Next question. How many flip-flops are needed to produce a divide by 128 device? You can also write this as mode 128 device. So if n is the number of flip-flops, then the relation is 2 raised to n should be greater than or equal to this mode value. Okay, mode value. This is the relationship. Okay, here the mode value is 128. So we have to try for various values of n so that the 2 raised to n value should be greater than or equal to 128. Now what is the value of n which gives us a value 2 raised to n equal to 128? It is 7. Right. So you can take 7 flip-flop to produce a divide by 128. So if it is some number greater than 128, say it is 129, then you have to go for the next number, 2 raised to 8. Anyway, that is not our question. Our question is we have to produce a mode 128 or divide by 128 device, means you have to select the n value or the number of flip-flops as 2 raised to n greater than or equal to the mode value or 128 here. Okay, so here the correct answer is option D, which is 7. 2 raised to 7 is 128. Okay. Next question. How does a queue work? Okay, so here we are going to talk about message queues or simply queues. So this queue, say this is a message queue. There will be a sender. So these are intercommunication, that is inter-process communication mechanisms. If you are talking about message queues, these message queues are used for sending of and receiving of messages. So they are inter-process or inter-task synchronization and communication mechanisms. That is, they are used for communicating between two tasks. One task is used for, one task uses message queue to communicate with another task. Okay, so there will be a sender task, there is a receiver task, and there is a message queue. Okay, so what will the sender do? The sender will put the message into the message queue. So the condition is that the message queue should not be full. There should be some vacancy inside the message queue, or some message spaces should be there for the sender to put the message. And also the receiver receives this message from the message queue. So this is the simple mechanism of the queue or message queue. So from this figure itself, it is very much clear that how the queue is actually working. Whatever message is first put into the message queue will go out first. So like this, the flow is happening. So we are putting the message to the message queue, and from this end the message is being taken. So we call this as head portion, and this is called tail portion. Okay. So this is all the very much details about the queue. Anyway, just understand that this is the flow of messages. So how the messages are flowing? It is flowing in the first in, first out. So whatever message is coming first to the queue, it will be get emptied first. So first in, first out, or FIFO is the basic principle of message transfer in a message queue. Okay. So what is the question here? How does a queue work? Option A, last in, first out. Option B, first in, last out. Option C, first in, first out. D, none of this. The correct answer here is first in, first out. And this is the simple working of a message queue. The sender is putting the message to the message queue. The receiver is taking the messages. So whatever message is being put first, it is taken first. First in, first out. Okay, so I hope this is clear. The next question is this. What are the states of a tri-state buffer? So what is actually a tri-state buffer? So actually this question is a little simpler. See here, it is given as tri-state buffer. Tri-state means 3 states, right? So this buffer, whatever it is having 3 states. Okay, so most of the options having 3 states. So you can't just answer from that statement. You should know about the tri-state buffer. So tri-state buffers are actually used as switches, which is used for passing a value from input side to output side with the control. So here A is the input side, C is the output, B is the control value. So you can represent the tri-state buffer like this. There is A, there is C, there is a B. So this is a switch. So these tri-state buffers are actually switches in order to pass one value from one side to the another side. We know the purpose of switches, right? So that is a tri-state buffer. Now what are the various states of a tri-state buffer? The tri-state buffers are having 3 states, a high value which is 1, a low, 0 and a high impedance state. High state, low state and a high impedance state. So this high impedance state is generally represented using Z. So in digital electronics, we represent high impedance state using Z state. Now how this high impedance state is indicated, we can study or we can understand from the truth table. Okay, so let this be A, value of B, then output side is C, right? So we'll give combination 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so whenever the value of, okay, we'll take this B as first 0, then 1. Okay, so it will be 0, 0, 1, 0, 0, 1, 1, 1. We'll like this. Okay. So when the value of B is 0, we assume that the switch, that is this switch is closed. Okay, when B value is equal to 0, we assume that the switch is closed and we won't get any output. Okay, so when a switch is open, when B value is equal to 0 means the switch is open. The switch is like this. That is, we won't get any output. Okay, so this is called Z state or high impedance state. Now, when the value of B is 1 means the switch is closed and whatever value we give to A will pass on to C. So, when B value is 1 and input A is 0 means output is 0. When B value is 1 and when input is 1 means output is 1. So, these are the 3 states and this is the truth table. So, high impedance state means when the switch is open. When you are applying a 0 to the B means the switch is now open and you won't get any output or the switch is remaining open. Okay, so it is a high impedance state, and when the switch is closed, whatever input is being applied, it will pass on to the output side. So when the switch is closed means now there is a connection path. So B value is equal to 1 when switch is closed. So I hope this concept is clear. Anyway, the Tristate Buffer, we don't have to discuss so much, but anyways, I'm trying to give you some concepts, right? So the Tristate Buffer is having what all states? High state, low state and a high impedance state. The correct answer is D, high, low and high impedance state. Next question. How many bits does a full adder K-map has? So we know that full adder means is having a A, B, that are the two variables to be added, and there is a carry in. So the full adder input variables are A, B and carry in, and it is having output variables as sum and carry out, right? So these are the output variables. So in full adder K-map, while drawing a K-map, we draw the K-maps using input variables, right? We are drawing the K-map of the full adder using the input variables, and from these input variables combinations, we'll get the expression for the output variables. That is a general case. So here, in order to draw the K-map of a full adder, we need a variable for sum, a variable for A, which is the first variable, a variable for B and carry in. So how many bits we need? Actually 3 bits we need. So the K-map is having how many variables? It is or how many bits they are having? It is a 3-bit K-map. So the correct answer is 3. And these are the 3 bits A, B and carry in. And we will get an expression for sum and carry out. Okay. So that is the case for a full adder. And the K-map of the full adder is having 3 bits or a 3 variable K-map it is. Correct answer is option B. The question that we are going to discuss today is this. If a 10-bit ADC is used to sense voltage between 0 to 3 volt, what is ADC resolution? A. 2.92 millivolt, B. 300 millivolt, C. 2.92 microvolt, D. 1 bit. Okay, so we can express ADC resolution in terms of bits and also in terms of voltage. That is the minimum voltage the ADC can detect, or the minimum change in voltage the ADC can detect. So in terms of bit, if n is the number of bits of ADC, then 2 raised to n is the ADC resolution. In terms of the resolution in terms of voltage is expressed as the maximum voltage Vmax by 2 raised to n. Okay, so here 0 to 3 volt means Vmax equal to 3 volt by, it is a 10-bit ADC by 2 raised to 10. Okay, so this is the ADC resolution in terms of voltage. Okay, so this is the equation to find the ADC resolution in terms of voltage, and if you solve it, you will get the value as 2.92 millivolt is the ADC resolution. The correct answer is option A. Next question. What is the BCD code for 21 to the base of 10? That is, if decimal value of 21 is converted into BCD, what will be the result? So we'll do simple BCD conversion. That is decimal to binary conversion we'll be doing. So 2, then 10 remaining is 1, 2, 5 remaining is 0, 2, 2 remaining is 1, 2, 1 remaining is 0. So the answer is 10101 is a representation. That is 10101 to the base of 2. The answer is C is your correct answer. 10101 is the BCD representation of 21 to the base of 10. The correct answer is option C. Next question. What is the operation of below circuit? So this is the circuit below. I hope you can see this circuit clearly. So it consists of an op-amp with a capacitor connected to its feedback circuit. Okay, so there is a capacitor in the feedback circuit and it is a op-amp. So this is actually a integrator circuit. So what is an integrator circuit doing? Integration means summing of your input signal to a particular period. So for a particular time period, you will sum the signal and then this is taken to the output side. That is integration in mathematics also, right? So what will this circuit do is, the Vin is making the capacitor charge. that is equal to summing. The value is getting added to the capacitor's charge till a particular time period, and then after that time period you will get your V out. So that is simply integrator circuit. So the options given are A integrator, B summer, C differentiator, and D high pass filter. So this capacitor with an op-amp circuit is actually an integrator used for integrating of your input signal for a particular time period. So this B is making the capacitor charge and discharge according to this time period. So it is actually a integrator circuit. Okay, so the correct answer here is option A is the correct answer, which is integrator. So these are the questions which we are discussing in this video. We will be doing the part 2 and part 3 for discussing the questions from this examination for technical assistant, that is NESAC examination. So this will be very much relevant if you are anybody who is preparing for the upcoming ISRO technical assistant examinations for the various locations. Okay, so I hope this video was useful for your preparation. If yes, please do give it a thumbs up and also share this video with maximum of friends who is preparing for the examination. And also, if you are somebody who is looking for the answer key, and I don't know whether the answer key is out or not. Anyway, if you are looking for the answer keys, and that is if you have written this examination, if you want to verify the answers, please do have a look. Okay, so if you want more videos also, please do subscribe to the channel. Thanks for watching and keep on watching.